Bienvenidos todos. Ya está con nosotros el doctor Leslie Lamport, está en una de las salas de Room y ahorita ya entra con todos nosotros. Gracias por aceptar la invitación y a estos nuestros seminarios, SWIT, Seminars with IT Pioneers and Leaders. Entonces, tenemos al doctor Lamport, que lo que es conocido por látex. Sin embargo, tiene muchísimas otros reconocimientos. Tiene su doctorado y creo que son 4 o 5 doctorados honorarios, más es un premio Turing, como el premio Nobel, entonces, más muchos otros premios Distra y muchos otros premios que tiene. Tiene unos algoritmos que se llama el panadero y entonces ya se están acercando, ya están viniendo con nosotros.
Here, teacher.
Yes. Thank you very much. Thank you, Dr. Leslie Lamport, for being with us in this SWIT seminar. And now I'm going to share. And this is the SWIT program. And seminars with IT pioneers and leaders. And as a first, let me check. We are asking, in which city are you in now, everybody? Can you answer the menti.com and use this code?
I'm sorry. Oh, are you asking everybody that question or just me?
Everybody.
Okay. Well, I'm in Palo Alto, California.
Okay, thank you. Is to know where are everybody. Oh, in Monterrey. Have you been in Mexico, Dr. Lamport?
Not for about 50 years.
Oh.
And I liked it very much when I was there, but
you need to come.
Somehow just never gotten back.
Oh. These are the cities in Monterrey mainly, and Guadalajara, Oaxaca, Atotonilco, El Grande, Hidalgo, Monclova, Coahuila, León, Guanajuato, Veracruz, Ciudad Juárez, Los Ramones, Tuxtla Gutiérrez, Chiapas, Durango, Tlaxcala, Tula, Hidalgo, Durango, okay, Mexico City, Ciudad de México, Colchester, okay.
Well, the only ones also in Guatemala. The
Guatemala.
only cities I remember being in are Mexico City, Oaxaca, and forgotten the other one, but it was the one near Mexico City.
Okay.
That went by.
You need to come back. Okay, thank you very much. And let me. We are going to start. And
Tijuana also.
Tijuana. Okay, you need to come back to come to Monterrey.
Mm-hmm.
Okay. And thanks to Dr. Leslie Lamport for being with us in Tecnológico Monterrey, Mexico. Thanks to Dr. Manuel Sartuche, Dean of the School of Engineering. Thanks to Dr. Joaquín Acevedo, Dean of the School of Engineering in North Region. Thanks to Dr. José Alfredo Galván, Director of Division in North Region. Thanks to Dr. José Antonio Rentería, Director of Division in North Region. Thanks to Ingeniero Luis Ricardo Salgado, Director of the Computer Department. And thanks to Montserrat Cruz, coordinator of SWIT, Seminars with IT Pioneers and Leaders, who has coordinated the conferences with Dr. Robert Metcalf, Dr. Steve Croker, Dr. Leonard Cranrock, and Dr. Taher Al-Gamal. And Dr. Bryn Cerf was with us in 2018. And thanks to everybody in this session. I am Rafael Davalo, leader of the SWIT program, and we appreciate your time and effort to be with us. Welcome, Dr. Leslie Lamport.
Thank you.
Thank you. We are in a question and answers.
Now,
Okay.
thank you. Yep. Yeah. So for you to ask a question, you need to, and I'll be calling you everyone.
Well, yes, don't wait for me to say anything because I'm just answering questions.
Any question?
Hello,
Okay.
my name is Marcos. I really admire Leslie Lamport since 1994 when I studied my first master's degree. I studied the clocks algorithm. I remember reading that paper. And then later on reading the paper of Dijkstra's improvement to the clocks algorithm. I used to teach distributed system class for several years in Tech of Monterrey. And I always refer to your papers, your research papers. So it's just an honor to be in this session with you. And I would like to know if you can share your experiences on the clocks algorithm, time and clocks algorithm back there.
I'm not sure there's much experience to share. Well, as Jim Gray said to me, not long after that paper was published, that he had heard two reactions to it. Some people said that it was brilliant, and some people said that it was trivial. And my reply to that was that I can't argue with the latter, and I'm disinclined to argue with the former. It just seemed very obvious to me. And it was inspired or stimulated by receiving a paper by Robert Thomas and Paul Johnson. I was actually just looking up that paper again. It was called The Maintenance of Duplicate Databases. And they had an algorithm that, I mean, there was a whole bunch of stuff in that paper, but at its heart, there was an algorithm that was sort of like the one in the Time Clocks paper, but they didn't quite get it right because their algorithm basically allowed commands not to be executed in causal order. And so I wrote, well, the two things. First of all, I corrected their algorithm. And in doing so, I had to explain, what causal order is. Basically, the happen before order that's defined in the paper. And also, one thing that they didn't say, and I'm not sure if they realized, but I suspect they didn't, was that the idea of what the algorithm could be used for is not just maintaining a duplicate database, but implementing a shared distributed state machine, and how the a shared state machine allows you to basically implement any kind of synchronization that you want in your system. And what I also realized is that if you're building a single system, then the best way to think about it is to think that you need to implement a shared state machine. And that idea has been actually the most important practical idea that came out of that paper. I mean, that's at the heart of things like Paxos and Byzantine generals and stuff. The amusing thing about it is that at the time, well, first of all, some people just thought it was about a distributed mutual exclusion algorithm. And some people thought it was just about the happens before order. And nobody, or hardly anybody, seems to have noticed the state machine idea. And in fact, on 2 separate occasions, people have told me that there was nothing about state machines in that paper. And I had to go back and look at the paper to convince myself that I wasn't crazy, that it really was about state machines. So the origins of the paper are, nothing much to talk about. I suppose it's what happened with it or how people reacted to it is more interesting.
Thanks for sharing.
So for you to ask a question, you need to raise your hand with the Zoom option, and I'll be calling you.
Maybe if nobody wants to ask questions, should choose someone and ask them a question.
Maybe.
That,
Okay, thank you. My question is having studied mathematics, do you think it's a big difference of coming with a completely different education? Let's say that having studied mathematics, do you think it really has a positive effect on theoretical computer science as a discipline? What would you say about studying mathematics against computing?
well, by the way, I have no idea who was asking the question. It would be helpful if you at least introduced yourself and if your picture could appear on the screen, but I don't know. I'm not capable of doing that.
Okay, it's me. I'm Javier. I'm part of the faculty here at the Tec de Monterrey and theoretical aspects of computing. Yeah, that's why I'm asking.
Well, as you've seen TLA or TLA plus, you'll realize that I've spent the last 20 or so years trying to get engineers to think mathematically about what they're doing. People talk about computational thinking, and that, well, that could mean 2 things. One part of it is there's a certain notion of thinking in terms of thinking basically about what one is doing, which is that one is thinking about things that change dynamically, but change discretely. But the bad way of that, to interpret that is thinking in terms of programming languages. And I find that thinking in terms of programming languages is not a great idea, certainly not when you're not writing a program. And if you're writing an algorithm or designing a system, you're not writing a program, you're not writing code. You're creating a design, and you should be thinking above the level of programming language to do that. And a problem that many, or perhaps most engineers or programmers have is they don't have the background to be able to think mathematically. I mean, they don't have the mathematical background. So there are a whole bunch of concepts, propositional logic, for example, that should really be second nature to an engineer, and aren't, because they haven't really absorbed the math that they need. And I will say that mathematicians are at least as much responsible as the engineers for that. Engineers aren't motivated to study, or at least computer engineers aren't motivated to study the mathematics, and mathematicians don't know how to motivate them. But certainly, nothing I have done could I have done if I didn't think like a mathematician.
Great, thank you. Thank you very much for your answer.
Now, Maddie.
Okay, it's me. Hello, Dr. Lamport. It's really great having you here with us. It's really an honor, really. And it's really exciting. I mean, talking to someone that basically inspired a lot of people. I mean, reading your papers was always great. Actually, I'm actually now teaching distributed system, like when the course is available, actually. So actually, just to tell you a little bit about it, in the course, of course, we study some of your papers. I mean, you can't avoid, talking about distributed system. I'm not talking about your great contribution, of course. And my question is, the first one is, I don't know, it can be a silly question. So when, for example, in the class, I asked some of my students to present and study some of the papers and present them. So when they get to read the Paxos paper from you, okay, sometimes they get confused, okay? And most of them actually find later on Raft protocol is slightly easier to understand. I mean, do you still feel is it really hard to understand, or the problem is from the readers, the Paxos?
Well, first of all, you should probably teach them not from the original Paxos paper, but from Paxos Made Simple. Yeah. I've difficulty understanding the difficulty people have with understanding Paxos. As to Raft, but I mean, this whole notion of understanding is a rather slippery one. I don't know if the initial Raft paper that I saw before it was published, they said that one of the advantages of Raft is it's easier to understand than Paxos, and they gave data with is that in the final paper too? The Raft paper?
Yeah, in the Raft extended paper in search of an understandable consensus algorithm, they mentioned that.
Yeah.
In
Well,
the extended version.
Well, they have these classroom, this class of students who said, yes, they understood Raft and it was easy to understand. Well, that algorithm that they understood had a bug in it. And that bug was found and fixed, I believe, before the final paper was published. But, you know, did they understand the algorithm if they couldn't see a bug in it? So, you know, understanding is what they mean by understanding is really, in some sense, having a warm, fuzzy feeling. And that means being able to relate it to things that are the way you think about things. And if you think about things mathematically, Paxos is very simple. And thinking about mathematically doesn't mean, you know, knowing advanced mathematics. It is just being able to think very precisely, you know, in terms of very simple concepts, you know, things like sets or, and when you think about it, you know, you can think about it that way. It was very simple. I mean, I can explain Paxos. I remember one time when I was attending a PODC conference, and you know, someone said that, oh, you know, Paxos, you know, seems difficult, and you know, just talking, you know, no board or no anything. In 5 minutes, I was able to explain Paxos to her, and I believe she understood it. But I expect that this was a computer scientist, and I think she probably had the ability to think mathematically and to think in terms of, you know, mathematical concepts.
Thank you, Doctor. Actually, to be honest, I was not so happy seeing that something like that in the paper, but I mean, it doesn't really make much sense, including something like that and concluding on a strong statement that's easier. But I just think maybe there are a lot of actually graphical explanation and like codes and things, maybe that make people or like students feeling just a little bit more comfortable with that. But the main question actually I wanted to ask you is, do you, about the current state of distributed systems, do you think there is anything overlooked in this field that people are not much paying attention, or is there any like area of opportunity that you encourage like future researchers to pay attention to or look into?
I haven't been paying attention to what's been going on in you know, distributed system theory for the past 15 or so years. So, you know, I can't answer the question about, you know, what's happening now. By the way, to say a little bit more about what we were talking about in understanding, one of my favorite quotes is from a cartoonist who said that writing is nature's way of showing you how fuzzy your thinking is. Because you don't really understand something, you know, unless you've written it down. And what I add to that is that mathematics is nature's way of showing you how sloppy your writing is. That if you really understand something, you can express it mathematically. So you know, if at least, I don't know how they test, you know, how they tested people's understanding of Paxos, but you know, the only way to test somebody's understanding is to have them explain it in writing.
Thank you so much for your time.
Alfonso Garza.
Hello, good afternoon, Dr. Lamport. Nice to meet you via Zoom, but it's something incredible. And I mostly know you because of the LaTeX system. So I'm a great fan of this programming language. I really love it. I think it's incredible and it's really useful. You know, not only on the science fields, but in engineering or where else. So my question is, well, I believe that when you create something, when someone creates, you know, a tool or whatever, there's a need, right, that you want to solve. So when you first started working on the LaTeX system, which was the need that you identified and that, you know, that you said, okay, if I create LaTeX or I work on this, I will solve this need. What do you think it was? Thank you.
Well, it's very simple. I was planning to write a book, and I decided to do it in tech, and I needed a set of macros. And I decided that as long as I was writing the set of macros for myself, I might as well spend a little extra effort and you know, make them useful for other people as well. And this was fairly soon after, well, I guess it was Tech 83 that you know, was the official name of it at that time, of the, you know, the final version of Tech. And I mean, I realized that, you know, Tech was a great system, but it really needed, you know, a layer above it, you know, set of macros. And yeah, I had a hunch that you know, LaTeX would you know, could be the system that you know, everybody would use who wanted to use tech, and it's pretty much turned out that way. I think the reason it was successful probably has a lot to do with the way I think. And I believe I've heard that Dijkstra said that I have a very good ability at abstraction, and a compliment like that coming from Dijkstra, not that he would have told me to my face, but a compliment of that coming from Dijkstra is you know, is very nice. And that what I tried to do was really abstract the basic concepts of what you're doing when you're creating a document, and put that into the macros. And of course, I stole a lot of the ideas from Scribe, which I guess nobody is. It's mentioned in my book, but I don't think anybody has heard of Scribe. Nobody your age would have heard of Scribe. But it had the basic idea of expressing that thinking in terms of the logical concepts of a list or a quotation or something, rather than in the visual appearance of it. And that's what I try to to do with tech. And because of both the nature of tech and the nature of the problem, I don't think I was able to do a terribly good job. But I think, it was pretty good given the circumstances and what it was trying to accomplish. And so, yeah, that's what happened. And I also had the good sense to give control of it to other people and let them worry about, maintaining it and improving it.
Thank you very much.
Ulises Lugo.
Hi, Leslie. Yeah, I just have one question. So I think you like to read, right? You have a lot of books in your back. So what's the one book you have read the most? And if you think about it in another way, it's like if you suddenly had like were away of your house and you just want to buy a book that you've already read or written, like which one would be?
Oh, that's a tough question. I mean, most of what I read, non-scientific stuff is fiction, and I would not. I mean, it was senseless to try to pick one book. But I will mention one book that I will tell you because you've probably haven't heard of it. And the writing is magnificent. And it's called West with the Wind, West with the Night by Beryl Markham. It's the only thing she wrote. And yeah, it's just amazing. And it's nonfiction, actually, but the writing is just incredible. Every once in a while, I take down that book and just read some random passages in it and just feel so bad as why isn't my writing anywhere near that good? I mean, I happen to be a very good technical writer. I'm a very good writer as a computer scientist, but just nothing. I just wish I could put the excitement into my papers. Just that a good author, a good writer can put into their fiction.
Thank you. I think you put that into LaTeX and into every algorithm you make, but thank you.
And, I mean, one piece of advice that people ask me, students ask me, and what I tell them is, well, if people ask me what I do, well, they'll think, oh, I'm a scientist. I, do this or that. But what I really am primarily is a writer, because nobody would know anything about what I've done if I didn't write it. So, primarily I'm a writer. In secondary form, I'm a performer because, I give talks, or not much anymore, but give talks about what I did. And so what I find is the most important advice I can give to people is to write, is to learn how to write better. And that the way you learn to write is by writing. You know, when you sit down and write a paper and you find it difficult, a lot of people find writing difficult. Well, they find writing difficult because they haven't done enough writing. It's like, being told that you have to run a race and you haven't done any running. Well, you need to build your writing muscles, and you need to do it by writing a lot. But you also need to pay attention to your writing and learn to write well. And the way you do that is to make sure that everything you write is well written. And I mean everything. So if you send an email message, don't just dash it off, but you write it and then you reread it and then say, is it exactly, is it easy to understand? Is it well written? Does it say what you mean? Could it be misinterpreted? And then is it just good writing? Is it something somebody would want to read? And just keep doing that. I mean, I've probably written thousands of pages of stuff that was never meant to be published. Because when I would sit down and start working on any kind of problem, or going to build a system or something, I would start writing down my ideas about what it should do. And that's what I advise students to do and to learn how to do.
Thank you, Doctor. Paulina Jimenez.
Hello, sir. I am Paulina. I am a student from Monterrey. And actually, my question kind of connects with your answer, because my question is, with all the experience you've gathered over the years, what advice would you give students who want to follow the same career path as you, besides writing daily, as you said before?
Well, no one is going to follow the same career path that I followed. I mean, it's not that you can't step in the same river twice, but the river has changed an awful lot since I stepped into it. It started out as a small stream, and now it's it's a very big river. So I can't give you career advice. The advice I can give you are things that your mother could have told you and perhaps did, which is always do everything make everything you do the best you can do. Don't be satisfied with anything. Anything that is not as good as you can do. When you write something, just go over it and rewrite it until it is as good as you can make it. That a teacher of mine once said that you should judge an artist not by what's hanging on their wall, but by what's in their wastebasket. So, just think about that before you hang something on your wall.
I will.
And,
Thank you, sir.
and again, also, you know, if you're doing, you know, anything in computer science, make sure you have a really good math background. And again, that's not so much in, you know, subject matter. I mean, you know, I don't think I've ever used algebraic topology in my career, but the skills that I developed in learning algebraic topology, you know, the ability to think in those terms, is what I use every day.
Alexander.
Hello.
Hello.
My name is Alexander. I'm a second semester student in Tecnológico de Monterrey. And well, I have actually two questions. One of them, partially you already answered regarding the math background for the computer scientists. But I wanted to emphasize for us, I'm only on second semester and we barely saw the computer science. We're mostly on physics and the mathematical part now. But I wanted to ask you, what do you think is the key, maybe book or the key part of the successful or a good computer scientist is? What maybe nowadays many of them missing, or what is your opinion on that? And the second question would be, since now we're writing a lot of stuff for physics and mathematics, and I really like to make my papers in a good format and all that. And a friend of mine recommended me using LaTeX, and I've been all in that and trying to encourage my other group members to start using it. And I was thinking what question I could ask regarding the LaTeX. And one thing interested me the most. When you created LaTeX, have you had this intention to make it Turing complete, or it was first as like a markup sort of tool?
Well, it's Turing complete because tech is Turing complete. I guess, yeah, I guess I introduced some macros that are, well, basically to turn tech as a Turing machine, you know, sort of, you know, to make it, to allow you not to have to program it as a Turing machine, but as something that looks a little more like a programming language. So, you know, with an if then else statement and a while statement, and I suppose that's in the book, but you know, that's really should be just for advanced users or users who are doing something, you know, really something special, or it's sort of, you know, it's more for people who design document styles rather than people who write documents. Now, you'll have to briefly repeat your other questions.
My first question was, which was partially answered already, regarding what do you think is the key part for the successful computer scientist?
Computer scientist. Again, it's sort of, you're asking me a career question, and you know,
not from the career side of it, but from as a skill, or as a, yeah.
Well, I mean, I've spoken about the mathematical skill that you need, and of course, you know, you need programming skills, and the mathematical skill is that one needs. I mean, it's in some sense what abstraction is about. It's not knowing the math, but it's knowing how to use math to describe the things that you're doing. the things out in the world. I remember reading somewhere a long time ago that the thing that helps children learn math best are those word problems, where, not asking them to add, 2 plus 3, but saying, if I've got 2 cookies in my left hand and 3 cookies in my right hand, how many cookies do I have? That sort of thing. And in some sense, what I've done is, in a lot of instances, is really showing how to do the equivalent of taking a problem, like, how many cookies do I have, and turn it into an addition problem, is to take a problem, in programming and turn it into a mathematical problem. And that's, I think, a very, very important skill. I don't know how one learns it or how one teaches it. So, I think probably computer scientists and mathematicians should get together, or computer science teachers and math teachers should get together and try to figure out, how that can be done for computer science. I mean, it's just like a physicist will naturally just think in terms of mathematics, trying to describe something. It's practically what physics is about. It's writing equations, to describe physical systems. Well, computer science can be as much, should have as much mathematics in it as physics does. Now, physics is not all mathematics, nor is computer science all mathematics, but it should have as much a mathematical background as physics does.
Thank you.
I mean,
oh, sorry.
One of the great problems that's clearly facing computer science is understanding machine learning, and that that's going to come from learning how to from learning the mathematics behind it, not from dissecting brains.
Thank you.
Okay, Daniel Diaz.
Hi, my name is Daniel. So when I was in high school, I wanted to study mathematics, but the notion I had of it at the time was more like it will be really difficult, like to find practical areas, in the real world to apply it. So I had a really poor mind at that time. So I ended up studying computer engineering. And now that I'm in the career, I realize, as you already mentioned, actually mathematics and computer engineering are really related. So probably I'd like to pursue now a master's degree in mathematics. So being said this, I just wanted to ask you, how did you decide yourself when it was your time to go for mathematics as in university, as a master's degree, and in your PhD? And how after that you decided to go for like the computer software field instead of, or rather than of other scientific areas?
My own history is, I mean, I could describe it, but it is very idiosyncratic. I mean, I started basically, math was my love through as a child, and it was a fairly obvious thing for me to major in school, and then I go to graduate school, and the reason I wound up teaching, doing computer science rather than becoming a math teacher is, has, it was almost by, almost by accident, or had things been slightly different, I might not have gone into computer science. But the reasons were, particular to my situation at the time, and not particularly relevant to anyone else.
I understand. Yeah. Also for us, it's that way. We need to take advantage of the opportunities that life presents us. So thank you so much for your answer.
I mean, the one lesson I would give to people, especially if undergraduates, is your undergraduate years should be to get an education, not to get job training. And computer science majoring in computer science these days, it seems to me that it's more job training than education. And you should take the opportunity to just study, to get as good an education as you can, taking courses and whatever you will enjoy, because you're not going to learn something if you're not enjoying it. But to try to broaden yourself, because the world, you're going to encounter in 50 years is going to be a lot different from the world you're going to encounter, when you get your degree. And there's no way of knowing what you learn, what of the things you learn now will be helpful in your later life. But a good education is always good.
Yeah, that's right. Thank you so much. That was really enriching. Thank you.
And we're having the last question from Juan.
Hello, Dr. Lamport. How are you? You have an incredible trajectory in computer science, and you achieved many goals as a professional in your career. Did you find a way to balance your personal life with your professional life? And if you did, what advice would you give us to achieve our professional goals and maintain a good balance in our personal life?
Oh, I do not feel qualified to answer that question. I think when I was younger, when I was your age and a decade older perhaps, I spent, I would say, most of my energy on my personal life, because doing computer science seemed so easy to me. Dealing with people is relationships, that's hard. Computer science, it was easy for me, but everyone is different. I can't generalize from my experience to in any way that will help others.
Yeah, Doctor, do you think we have time for one more question?
Yeah, I mean, we don't have to stop, right at 1 o'clock.
Okay, Edgar Alan.
Hi, Doctor. I would like to ask you a specific question, like, could you please share any words that do you think will motivate young scientists and like to pursue a research career? Thank you.
No, I mean, I don't want to inspire, or, well, I don't want to convince people to become computer scientists or to do anything. You have to want to do it. Whatever you do in life has to be something that you love, that you want to do. Now, if I've inspired you to love computer science because of what I've done, well, that will make me very happy. But I shouldn't have to tell you why to become a computer scientist. If you want to be, if you don't really want to become a computer scientist without my telling you, then it probably means you should be doing something else.
Thank you for your answer, and to be honest, you really do inspire me. Thank you.
Thank you.
I would like to make a question.
Sure.
And okay, how can you summarize the bakery algorithm, and how do you get it?
How do I summarize it? You said.
Yeah.
Yes. Oh, yeah. That's a very straightforward. I mean, the ideas. I mean, do people know what the bakery algorithm is? Do people know what mutual exclusion is? Nod your head if you do, or no, or the other way if you don't. I don't see many heads nodding. Well, a few. Well, okay. The problem is you've got a bunch of computers that say that all want to use a printer, but they can only use them, one at a time. So, how do they organize themselves to do it? And the idea of the bakery algorithm comes from, a bakery in my childhood, where people would enter the bakery, they would take a number from a machine, a tick machine, and then, people would get served at the counter according to in the order of the number they picked. And the bakery algorithm is, well, it's easy then to solve this problem and computer science, with computers, if you have one process that's that serves as the ticket giver, and so everybody goes up to him and asks for a ticket, and they get it, and that's fine. But Dijkstra posed the problem, and it is a brilliant paper proposing the problem, because in that paper, he did all of the requirements that he he made prevented trivial solutions. And they were all significant requirements. And one of them was that, there shouldn't be, any computer that wasn't interested in printing shouldn't have to do anything. And, particular, it shouldn't have to ask for a ticket, or you shouldn't have a process that has to sit there and just give tickets. And there, so the bakery algorithm is everybody comes in, chooses their own number by looking at everyone else who's waiting to be served, and then choosing a number that's bigger than any number that he sees. And it turns out that, you see very obviously, if two people are entering the bakery at the same time, they could choose the same number. So you break ties by using, the name of the customer. If two people have the same number, they go in alphabetical order of their names. And it turned out that if you just write that algorithm down and look at it, you'll see that it doesn't work. I mean, you have to just make a very simple, and you see why it doesn't work. You just have to make a very simple addition to it. Basically, to make sure that you don't try to read somebody's number while he has just entered the bakery, but hasn't chosen his number yet. And so if you wait until, if you don't read somebody's number while that they're doing that, then it works fine. And that's the bakery algorithm.
Okay, thank you very much.
And the last question from Adolfo Cabrera.
Hello, Doctor. My name is Adolfo Cabrera from the Master's in Computer Science. We have been talking about writing nowadays. There are outside machines reading the internet and learning how the humans write, literally from literature to code. And I would like to know your opinion about how do you perceive this change in which the computer scientists are becoming data experts?
What experts, you said?
Data experts.
Mm-hmm.
How you think about it? What is your opinion about these new changes that we are living?
Well, I guess, what do you mean by a data expert?
I mean, in the past, we perceive more the computer scientist like someone that write code and used in mathematics and everything you expressed before to create algorithms. But right now, in the media, on the academic, there is the perception that it's nowadays more important, the data and how we can handle this kind of systems, the machine learning. And this is how I would like to know your opinion about these new changes.
I'm not sure I see any change in that regard. In the old days, people were, writing programs for banks, and big thing was, how do you maintain the bank's data? And now, the data is, pages on the web, but I think the biggest change in computers is simply who's using them. You just need different programs from, whether a banker is using it or whether your grandmother is using it. And, that's made a very big big change, but I don't see data as being, significant in that regard.
Thank you, doctor.
Okay. Thank you everyone for your time. That's it for today. And thank you, Dr. Lamport, for sharing your time with us.
Thank you.
Thank you. Thank you very much.
Thanks.
Thank you for your time.
Thanks.
Okay.
Thank you so much.
Goodbye.
Goodbye.
Bye.
Thank you.
Thank you.
Bye.
so
Thank
much.
you.
Bye. Thank
Bye.
you.
Gracias a todos y nos vemos en la próxima. Hasta luego.
Hasta luego. Muchas gracias.
Gracias. Hasta luego.